We are back once again. It is day 81, right? Day 81 of daily LeetCode. So yesterday we did number of provinces. Again, usually I do a union find based approach, but this time we kind of took a simpler approach with the BFS where we keep track of the parent array. That being the case, it looks like we're going to be battling our long-standing nemesis coin change again, right? So it's going to be interesting to see how we go about this, right? But we'll talk about that when we get into the problem. Other things, it looks like we're going to be averaging around 30 minutes to start these days. There's just a lot of other things I'm trying to get at. So you can kind of tell by all these tabs, there's a lot of aspects that I'm trying to make some progress on. And yeah, another takeaway from something I was listening to the other day, just listening to the same Lex Friedman podcast with John Carmack. And yeah, he was just mentioning some things that I think I struggle with as well. But he's mentioning that to some degree, right, after you're working on something for a long period of time, maybe 6 hours or something like that, right? After that, maybe the work you do after that is troublesome. Maybe you actually start going backwards. But to some degree, doubling those hours, because sometimes, right, you double those hours, maybe you're doing 12 hours, right? And you think, after a certain point, you're just wasting time or you're just going backwards. But I think there are some people who can do that 6 hours, right, double it to 12, and then still make more progress. But in another sense, even if you have 100% efficiency for 6 hours and then you drop down to 17 or 10% efficiency over the remaining hours, it's still more work done. And I think that's what he was kind of getting at in the podcast, that to some degree, even if you work longer hours, if you want to get something done, working more always gets you there faster. I think that's something I struggle with a lot, since we tend to bounce for a while on the challenge. We were doing about an hour and a half a day. And even maybe a month and some change ago, we were doing like 4 or 5 hours a day. Then we got some really good practice in. Now we're slowing down. But slowing down on the LeetCode side, but ramping up on other sides. There's some other things I want to be able to create. So just something to think about, food for thought on the concept of a marathon versus a sprint. So yeah, something we're working on. So I'm interested to see. I know Thomas says he does like 2 or 3 hours a day. I know the Copy Ninja is probably putting in hours and hours of time as well. So I think in the Discord, you're going to find that a lot of us are putting in many hours a day, but don't feel intimidated by that. I think you got to start where you can. I personally started with like 15 minutes a day for a long time. And then finally, we got to multiple hours per day, but it definitely takes time. But yeah, it's just interesting. So we're back at coin change, right? And so that's what we're probably going to do today. Don't forget to join the hyperbolic coding chamber, right? We have just finished talks with some agencies. We're going to be routing even more services to the Discord because we're using so much bandwidth. The amount of people that are joining the Discord every hour is actually stressing the United States networking system. So the DNS servers, I don't even know if this video will get uploaded because the DNS server timeout is going crazy. So yeah, we're in hopes to increase the resources allotted to Discord servers. So yeah, you're going to want to join the Discord, right? Today is a limited time offer that you're going to be able to join the Discord with no wait time. Previously, this is actually true, by the way. Previously, when you joined the Discord, you'd enter a queue that would take many hours, right? So you're going to want to join limited time offer today to join the Discord, and you won't have to wait. So make sure to join. There's some cool people in there, a lot of cool people working on a lot of cool things. So hopefully we'll be able to fry all LeetCode problems in the future. But we're just going to jump into it. We have 30 minutes today. We're going to do coin change, and then we don't have any more cards due, so we're going to strike a balance between working through the problems quickly and verifying our assumptions and making sure that we're not skipping any steps. Because more than practicing for a long period of time, we want to make sure that we're practicing correctly first, right? So how we practice is probably more important than how much we practice. So that's what we're going to do today. So we're just going to jump into it. This is day 81. So You are given an integer array coins representing the coins of different denominations and an integer amount representing a total amount of money. Return the fewest number of coins that you need to make up that amount. If that amount of money cannot be made up by any combination of the coins, return -1. You may assume that you have an infinite number of each kind of coin. So this is an interesting problem, right? So basically, I'll make my camera smaller first. Basically, we have an array of coins, right? 1, 2, and 5. These are the coins that we're allowed to use, right? We can use them an infinite number of times. And we're trying to create the goal amount, which is 11, right? And we want to find the minimum number of coins in any order of these coins given. That will give us the amount 3. We know from this answer right here that the smallest number of coins we can use is 3, and the specific denominations used are 5, 5, and 1. So how do we go about solving that? Right? So there's one way that we can view it, and before we get into that, we have to look at some remaining examples. We have another example, right, where we're given a coin 2, right, but the amount we're trying to get to is 3. So presumably, right, the only coins that we can get to, or the amounts that we can get to using 2, would be pretty much a multiple of 2. And 3 is not a multiple of 2, right? Because all you can do is 2, 4, 6, 8, and so on. So we can't get to 3. So when we can't get to the number, we want to return -1. Similarly, right, if we have one coin, right, or any coin, and our amount is 0, we can always reach it, right, because we can just use no coins. So no coins is always an option. So that being the case, before we even jump into the algorithm, we know that for certain, right, if, right, we can just say return 0, a path, right, number of coins would be 0, right, if, and this is TypeScript, so we're going to change it to Ruby real quick. We're going to say return 0 if amount equals 0, right? Why is that? Because we can see in this example, right, when they want us to get to an amount that is no amount, we can just use no coins. And so we're using no coins, we have to return the number of coins it required to create the amount. And to have a 0 amount, you use no coins, right? So then how could we go about this problem? Well, we can phrase it as a graph problem. And the way we can do that is what we're basically asking, right, is given a tree, right, where each tree, the node that we're going to start at is basically 0, right? And you have 3 potential paths, right? And those 3 paths are going to be the number of coins, right? 1, 2, and 5, right? How many different ways can you solve it, basically? I mean, how many different paths, how many different options do you have? And you always have 3 options. For any given node, you have 3 options because there are 3 coins. And so basically what we're looking for, right, is the shortest path to a node, right, that ends at amount equals 11. So if that's what we're looking for, we could kind of rephrase this problem as shortest path, right, to 11 starting from coins, right? Because there are 3 amounts you can start from, either 1, 2, or 5, right? So these would actually have 3 separate trees, right? Because you can start from any of these coins as the starting point, right? So that being the case, if we rephrase it as shortest path, start going to 11, starting from each coin, right? We just could do a shortest path algorithm. But searching from our source, right, which would be 1, 2, or 5 to 11, means there could be an infinite number of paths. But what if we rephrased it as we start from 11, right, and we search for the shortest path starting from 11 to 0. And if we do that, right, we should prune our tree. We should be able to prune the number of paths we search a little bit. And that's because presumably there are less paths to 11 than there are paths to, you know, any number of different denominations, right? So this should simplify our search a little bit. And then the best candidate for shortest path algorithm is likely going to be a BFS, just due to the nature in the way that BFS algorithms expand by always processing the, so you push a node, or you want to visit our neighbors. We always process them in order, right? Because if we start at 1, we could take 1, 2, or 5, so we push 1, 2, and 5 onto the queue. Right, and so we always process the earliest nodes first, so it lends itself what any path, I guess, start a path, right? In a BFS, if we start at a particular vertice, right, V to start, and we do a BFS to find vertice, let's just say like, I don't know, V1 or V2, right, has to be the shortest path, right? And I think that is just a property of BFS algorithms. So I think we know that as soon as we find a path from 11 to 0, we know that that's the shortest path. So we know for certain that that's the shortest path. And I think that's just a property of BFS algos. So if that's the case, I think we could do this. There's another problem being that we need access to a queue or a deck, right? Because we need access, because the BFS, the version that we do at least, is used with a queue. So we need to be able to remove an element from the front in constant time and remove an element from the end in constant time, right? So we could do a version of this. The time complexity here always gets me, but let's try and do this version, right? So let's try and see if we can verify our assumptions going through. Usually we do a regular queue, right? And it's usually just an element within it. We want to start at 11, right? So if we want to start at 11, right, likely what we would have in the queue would be 11 to start, or basically amount. We want to get to 0. Right, how are we going to know our current path length? Technically, we could know our current path length by the level of the tree, but I think there's a simpler way. Path length by level, right? Because if we have a tree, technically the length of the path would also be the same as height, right? If we have, let's say, a tree like this, right? Is this a tree of height 3? Or is it a tree of height 2? So I think height usually counts number of nodes, not the edges. But in this case, if it is the number of nodes, then we could just return the level. But if it's not, we have to return the height. I mean, well, we could just return the height of the tree, or if it's just the edges, it'd be the height of the tree plus 2. In case we're looking for, let's say our amount was 9, right? 3 plus 3 plus 3 would give us 9. So if that's the case, let's go with a safer route. Let's just say, right, each number starts with a path length, right? It has the current amount and a path length, right? So I think that would be easier. So we have amount. I'm curious to see if Ruby has a deck implement. So Ruby does have a deck, so this is awesome. Apparently we can just do deck.new. So we can do deck.new, and then we can do add front. We're going to add amount, right? And its path is going to be 0, right? And then for the BFS, usually we say, right, while length does not, or while queue.length does not equal 0, right? Then we're going to take a current element, right? We're going to have the cur amount, right, and the path length. But for example, should the path for the first element, right, we have 11 and 0. Should 11 count as a node, like a part of the path length? Well, let's check. Let's say we wanted to get to 10, right? And let's say the coins we had were just 1, right? So we'd start with 11. We could maybe pull 11 off the queue, right? We pull it off the queue, and it's not a queue. Let's change it to deck. And let's just say we pulled 11 off, right? Now we want to visit our neighbors. The way we visit our neighbors is we just subtract, from the array of coins that we have. We only have 1, right? So we'll add a new element onto the queue, to the deck, and we're just going to add it with the value 10. And then we're going to say we're going to add 1 to the current path, which will turn this to 1, right? And so in that sense, it does look like we can start amount with 0. So the next path, right, on the next time we pull it off the queue, right, pull 10 off, 10 would be equal to 0, or amount would be equal to 0. So we should be good. So let's try that, right? So we're going to destructure here. We're going to say cur amount, right, and cur path is going to be equal to deck dot remove front, which I think is what they call it, remove front. And then, right, we're going to say if cur amount equals 0, right? Or we can just do return cur path if cur amount equals 0. Otherwise, we want to visit all of our coins, and we can say coins.each do, we'll say coin, right, coins.each do coin, right, and then we want to visit all our coins. And the way we would do that, right, we would push new values onto the deck. So we might say add rear, right, we're going to push another tuple onto the deck, and the goal here, right, would be to decrement from our current amount, right, so we'd say cur amount minus coin, right, with path plus 1. Our path is now longer. So I think this makes sense. And we'd need an end for a while. All right, and if we never find a path here, if we never find a path to 0, it means we can't get there. So we would return -1, right? Because like we said, when we can't get there, case of 2 goes to 3. And this is the other thing we have to check. Now that I'm realizing, how do we know we can't get there, right? Because we'll just keep going, right? We'll just keep going here. So one thing we're going to make sure we want to do, right? If cur amount, right, minus coin is greater than or equal to 0, right, then we'd like to do the work we mentioned earlier, right? Otherwise, we end up doing work infinitely, right? Because we're trying to get to 0. We can go past 0 and keep going, even though we'll never reach 0, right? Let's say we get to -1. We keep decrementing. We're not like -1 trillion. We need to stop, right, when the potential to go, once we reach a potential to go past 0, we want to stop. Or we don't want to add that to the rear. Or we don't want to consider it as a possible path to continue searching. Say cur amount minus coin is greater than or equal to 0, then we're good. Then add to the rear. Remove front. So let's see if this works for 1, 2, and 5. We're going to push 11 and 0 onto the deck. Deck isn't empty, right? We'll take 11 and 0 off. 0 does a current amount, which is 11 equals 0? Nope. So for each coin, we're going to do cur amount minus coin is going to be greater than 0. Now we're going to add 3 new nodes to search, or neighbors. 11 minus 1, which is 10. 11 minus 5, which is going to be 6. And 11 minus 2, which is going to be 9. So we're going to have 10, 9, and 6. And then from 10, we're going to go right. So we're going to have a path length of 1. Right, none are equal to 0. We're going to do the coins for 1. Right, we're going to do, we're at 10. Right, we pulled 10 off the queue. So then we have 9, 8, and 5. And this seems to be panning out. So I want to maybe make the example a little simpler. Let's just say we had 11 and 1. But even then, that's still a little bit much. I don't know if there's a smaller version that we can do. I kind of want to hit run, but we should verify that this makes sense. We have 11, right? Pull 11 off. 0. Right, 11 doesn't equal 0. Let's just say we only have the 5 as a coin. For each coin, right, 11 minus 5 gives us 6. So we add 6 with 1 onto the deck. Right, and then we have 6 and 1, we pull it off. 6 doesn't equal 0, so we do coin dot each, right? We do 6 minus 1, which is greater than or equal to 0, so we're still in business. And then we do deck dot add rear, right? 6 minus 1, which is 5. So then we add 5, and we have we had 1 onto the deck, right, with a path of 2. Right, and that's the only neighbor we have. Then we take 1 and 2 off of the deck. We destructure. 1 doesn't equal 0, right? And now we're going to go past it, right? So cur amount minus coin is not greater than or equal to 0, so there's nothing to do. So we eventually return -1. But if we had 1, we would have reached it. So I think deck.remove front. Unexpected. Interesting. How do we go about this? Unexpected equal. Expecting end. Deck.remove front. We should just say item equals this, and then we'd say path, right, or cur amount and cur path equals item. Oh, I'm destructuring like in JavaScript. You don't have to use, okay, you don't have to use array brackets to destructure. Undefined method add front. Let me check. So we can definitely do add front. Maybe you just can't add. Maybe you just can't add. I don't see why you couldn't add a multiple. Right? I don't see why you couldn't add an array. I guess. Right. Let's just try add rear, or maybe you have to explicitly declare the size. That seems unlikely. I'm undefined method add. Oh, there's no deck. This guy just made a deck in Ruby. So we don't actually have access to a deck. So let's just do it how we usually do it, even though we won't necessarily get the performance we were hoping for, right? Because presumably we would want constant time insertion removal at the front, and constant time removal and insertion at the end as well. So we don't have, it's not too bad. We just have to change all these from queue to deck, and we could get an increase in runtime. So let's just check if there's no more deck. And we're still using remove. Man. Let's just say pop. And what we're looking for, is shift, because we want to remove off the front. What we want to do here is push onto the end. Turn cur amount. Okay, we do structure, and then we do cur path. If cur amount equals 0, coins.each, do coin. Undefined method plus for no class, no method error. Oh man, we are all over the place. The queue, we want to have an array of tuples, that's why that's nil. So we pull two values off of cur amount and cur path. So time limit exceeded. Dot. I think we ran into this before. We ran into this before in the optimization. I think we did was skipping coins that we'd already seen, which is very much still possible because we would be revisiting a lot of nodes. So we could do the same thing here. We'll say scene equals hash dot new. I'm lagging very, very badly for some reason. So I guess we'll try that. So do q.shift. So maybe after we do q.shift, right, we could say, right, we could say, or I don't think it's not called continue in Ruby, it's called something else, but we'll just say if not seen sub cur amount, right, then we'll do all these things up here. Otherwise, right, we want to skip it. And if we haven't seen cur amount, then we're going to want to do scene sub cur amount equal true. That way, right, we'll say, right, we've seen, we haven't seen 11 before, right? Now we've seen it. Right now we're going to visit our neighbors. We're going to push right on 99, right? 99, 98, 95. Well, those also might not be the best paths. So when we get to, let's say we get to 5, right, from visiting one way, I don't think scene is the solution. coin change is such a strange problem. This is a strange problem. We've discovered it. Don't want to use scene because if we visit 99, let's just say we visit 99 first. Maybe the way we got to 99 just wasn't the best way to get there. So we don't want to never include it again. Seems a little bit ludicrous. I remember what Thomas said about searching between source and target. And starting from target here should be faster. The tree is still massive. Maybe this is just one of those days. Yeah, I think I'm definitely having some transference or interference. I'm thinking about shortest path problems, but I'm also thinking about like 4 other problems at the same time. Just messing me up. I'm thinking of snakes and ladders, thinking of coin change. I'm also thinking of climbing stairs. These are all similar problems. I'm trying to reason about this. I guess I don't understand why I'm getting TLE. It could be because of the deck. I think it could be why. Could be. I mean, could be because of the queue. I think it might be because of the queue, and I think this is why we implemented a linked list before. I think that is why. I think that is why. It's strange that Ruby doesn't have a built-in, or maybe does. Let me check if Ruby has a linked list. We could quickly use. I was just looking. It doesn't seem to be the case. I think it's interesting. Yeah, I guess I thought more languages would have more built-in data structures, but I think it's interesting that that's not the case. I thought there might just be a linked list. Now that I'm thinking about it, in even in JavaScript, like I don't understand why there's not a native or built-in linked list or yeah, that's just very interesting. But maybe I think that was the solution to this, or maybe we'll just come back tomorrow and implement the linked list, which I think is what we did last time. But I think, yeah, this is a queue, and so the worst case, when we have, let's just say, a ridiculously large number of elements, and we do shift, we have to shift all the elements down, which means that every time we remove an element, it's like n. I guess, yeah, it could be like n squared. So we shift the first element, we shift them all down. Take another element, then we shift them all down. And then shift them all down, which means we had shifted all the elements down. We shift all the elements down n times. Or maybe. Yeah, it's very interesting. I'm very curious to see what I did last time. I'm pretty sure last time what we did was the same thing except with a linked list interpretation. Or like there was like a deck we built that was, but it's basically just a linked list. Very laggy. Sign of the times. Yeah, I'm pretty sure what we did last time was a linked list, and we just implemented it, because I remember us failing the first day and then coming back the next day and implementing the linked list. So, yeah, that is definitely interesting. I mean, this won't load, so I think we'll stop there today. But yeah, we're having an encoding overload issue, so we shall return tomorrow.